Let's take a look at more congruences. So there's the fact here. Now, we're not going to prove this, but I alluded to this, and we're just going to now state it as a fact, that if we take the union of all of these equivalence classes, or all these relation classes, these are forming the set of all integers. So modulo n, we have all of these together. So we looked at modulo 3, the union of the classes of 0, 1, and 2, that was equal to z. If you look at the say mod 5, then you take the relation classes of 0, 1, 2, 3, and 4. The union of all of those forms the integers, and we said that the intersection of all of these will not be, or the intersection will be empty, right? So there's not going to be anything in there. Okay, so definition. So if we have n be any natural number, the set of integers modulo n. So integers modulo n is what we're defining. This is the set z sub n, which is defined as all of these relation classes for the integers 0, 1, 2, 3, all the way up to n minus 1. So integers modulo n. So these are all of the relation classes, congruence modulo n. That's the relation we're defining on. So Z4, so we're talking about Z4. This is going to be the relation class containing 0, 1, 2, and 3. So that's it. So when we're talking about Z4, we're really talking about these 4 elements. Each of these elements is technically a set of a whole bunch of them, but there's really 4 elements in Z4. Now we could have also said this is the same thing as the set containing 4, say the set containing 9, the set containing 2, and then the set containing -1. Because we know each of these classes are the same, right? So this relation class is the same as this one. These are the same, these are the same, these are the same. When you're looking at these modulo 4, but this is the one that we're primarily going to use. Even though there's a bunch of different possibilities, we always just use this to represent 0, 1, 2, 3, all the way up to n minus 1. That's just the standard way of defining Zn. So Zn is going to be, it's super cool. This is going to be a whole lot of modern algebra. As I said, we'll be using this. Zn will appear all the time. So we're going to talk about operations on this. So operations on Zn, this is going to be called modular arithmetic. Modular arithmetic, it's really quite, I think, fun once you get the hang of it. So if we look at addition and multiplication, these are the 2 major operations we're going to define. Addition, so if we add 2 relation classes together, what we're going to be doing is just simply adding the numbers on the inside. So the relation, so here, if I look at the relation class of 0 plus the relation class of 2, that's just the relation class of 0 plus 2, or 2. Same thing as if I do, say, 1 plus 2, I'm going to get 3. Okay, now if I multiply these, I'm going to simply multiply the insides together. So basically, addition and multiplication are defined exactly the way that you would want them to, but our relation classes, remember, we're just going to be talking about these numbers. We don't really want to work with these ones that are outside of the range of 0 to n minus 1. So our goal is, after we do addition and multiplication, we're going to try to be able to break that down into one of these sets of 0 to n minus 1. So let's take a look at Z6, for instance. So when we multiply these, this is going to be the same as the relation class of 10, right? 2 times 5 is 10. But Z6, remember, this is going to be 0, the set containing 0, 1, all the way up to 5. So which of those relation classes is the same as 10? Well, again, we're talking about this congruence relationship. So if we think about these as remainders, when we divide by n, we take 10, we divide that by 6, our remainder is going to be 4. So this is the same as the relation class of 4. And remember, when we looked at the elements within these sets, when we listed all these out, we could add and subtract copies of n. So when we looked at this for 3, We looked at all of those sets. We had the set containing 0, and then we'd add 3 to get 3, 6, 9, or we subtract 3 to get -3, -6, -9, and that. Those are all of the elements in this. So you can just add and subtract copies of 6 until you get in that range of 0 to n minus 1. Now, multiply these two, I just simply get 0. Right, 0 times 1 gives me 0, so this is it. Now, 2 times 3, this is going to be the relation class of 6. Now, this is not a very large number, right? It's not like 10, for instance. But remember, we stop at n minus 1. So really, the relation class of 6 is the same thing as the relation class of 0. So maybe store this example in the back of your mind that you just said 0 times 1 is 0. You also said 2 times 3 is also equal to 0. That's a really good type of notice, right? That you now have two things that multiply to 0. You're going to have two things that multiply to 0. Okay, store that. So now, if we want to, instead of writing it this way, of always using our relation classes, a very popular way is to go back to our regular A is congruent to B mod N statements here. So if we're looking at 2 times 5, what is that congruent to mod 6? Well, that just corresponds to this number in the relation class, is that this is congruent to 4 mod 6. You could have said 2 times 5 is congruent to 10 mod 6, but you could also say that that's congruent to 4. Same thing, 0 times 1 is congruent to 0 mod 6, and 2 times 3 is equivalent to 0 mod 6. So that's what our multiplication in this case is saying. Addition works the same way, where you just simply are going to add these, and then you'd like to reduce this, so that way you're down within that range of 0 to n minus 1. And hopefully that gives you a good feel of modular arithmetic.